Mays South Elementary kind of heard about what we did and heard very good things, so they want us to do that same thing at Mays South Elementary. It'll be April 15th. They're doing a little bit later. They're from like 6 to 7:30. So if you're interested in participating in that same type of thing, especially from the Mays South crew, you know, since that's kind of your backyard. Anyway, so just kind of put that on your calendar. I think it's like a Tuesday night, and it'd be the same kind of gig. What?
We play soccer. I would go because like my little sister still goes there.
Yeah, right.
Oh, really?
Yeah, pretty spread out.
Okay. Anyway, just kind of put that on your calendar, and we'll see what happens from there. Okay. Also, and again, this is strictly optional. Okay, it's study session tonight. For those of you that are just taking the AP test, it's just kind of work through some old tests, kind of give you some strategies, that type of thing. Just so I know how many copies to run off, how many people think they might be here tonight? 1, 2, 3, 4, 5, 6. Okay, all right. Gives me a ballpark. So what happened, I'm gonna have that door propped open, so if you like walk out to here, see the fish tank, take left, there's an entrance door out there, I'll have that propped open. Look for a little gray Maverick parked right in front of the door. That's the one you come into, because that's my truck, and that's what you'll see. So that door will just, it's gonna look like it's shut, but there's gonna be a little wedge there, and you can get in that way. Like I said, we'll start about 6, last about 7:15, okay? Not a huge investment of time. I am not in the mood for this thing today.
You should try and do that. He just said he's not in the mood. That's why you should try and do that. He's already happy with you.
Oh, yeah.
He's really happy
So
with both
happy.
of you.
So
I
happy.
just put it in my.
Okay, so let's chit chat about the assignment from yesterday. And like I said, unfortunately, there is no shortcut to this. This is how chemistry is done, is that you look at the rates and you see how that's determined. Now, as you go through this, once you do the lab with this iodine, you'll see that the analysis is the easy part. The tough part is actually how do you get the data, okay? Because it's like, okay, if you look on these, this reaction on that second one on the yellow sheet on the front page, where you've got NO2 decomposing into NO and oxygen, okay? So when you look at this, first off, you're going to look at this and go, well, everything here is a gas, and how do you begin to measure that? Like, how do you physically measure the concentration of the NO2? A lot of times what you do is you measure the pressure, because as it's being consumed, the pressure is going to drop. But then that runs into a problem, because then you're producing NO and O2 on the other side, and then how do you measure that? That becomes problematic. So the analysis is the easy part once you figure out what happens to the concentrations. The tough part is getting the data to begin with. So conveniently, you're starting with the data, so you don't have to worry about that. So here's what you've got to do. So let me give you some hints. So on the first one, on the front of that yellow sheet, when I tell you to write, and you have to understand the terminology. When I ask you to write the rate law, okay, like for that first one, because it's just in terms of A turning into B, you should see that first off, that first one is first order. So your rate law is going to be R equals K times the concentration of A. That's it. That's all you have to do, okay? That's all you have to do. When I say write the rate law, that is all you have to have. And unfortunately, from the data that you have, you can't do the process where you run different reactions and you make things cancel out and all that good stuff, okay? It doesn't work. So with this one, you've got to measure the concentration as a function of time. And then you're going to draw a graph, and if you combine them together, where you have time over here, and then for whatever reason, I always put the natural log on this side, and then I put 1 over the concentration on this side. Your natural log tends to have a negative slope, and your 1 over concentration of A will have a positive slope. And so basically, you've got to look at that and go, hey, which one's going to be the linear function? And sometimes it's very obvious. Sometimes it's like, which one's the more linear? Okay? No, literally, that's sometimes you're going to get data. It's just like, I don't know. Neither one of them really are. What do we do now?
I like the sound effect.
Well, okay, I do what I can. I've been practicing that all morning. So, now, here's where you can look at your answers to see if they make sense. So, on number 5, where it says, what's the concentration of A after 100 seconds? So, if you go and look at your times, you know what the concentration is at 80. You know what the concentration is at 120. So, you know your answer has to be somewhere between 0.045 and 0.03. Okay? If it's not, you've done something horribly wrong. So your rate constant, which is the slope of that line, should be around 0.01. Okay? Make sure that you also have the correct units. Because it's first order, that it's the natural log versus time is the one that's more linear. So when you find that slope, okay, and you pay attention to the units. So here's the beauty of natural logs. That has no units, okay? Nothing. Once you take the natural log of something, the units go away. So when you find that slope of that line is just 1 over seconds, or you can put s to the -1, whatever you want to do. But again, this has to be consistent on how you apply the units. And even if you go back to the rate law, okay, no matter how, whether you're using the rate law or the integrated rate law, the units have to form this cohesive idea. So this K would be 1 over seconds, because A is your molarity, so that gets you molarity per seconds, which is what any rate is going to be measured in. So whether you're finding it by using the slope, whether you're doing dimensional analysis, doesn't make any difference. Now, when this gets a little bit mathematically challenging, is when you get to number 5 and you want to find the concentration of A after 100 seconds. So you've got the natural log of A, which is your unknown, and then you've got your slope, which is about -0.01, and you got 1 over seconds. And then you got the time of 100 seconds plus the natural log of your initial concentration, which is 0.1. Okay? So, how do you undo a natural log?
E to
E to that power. So and again, look at this holistically. Do not just get wrapped up in going, oh, I'm going to put numbers into a calculator and then don't look at your answer and go, how does this make sense? So your seconds are going to cancel out, so that has no units. That's the only way I can add that to the natural log of 0.1. Because if this did work out to have units, I couldn't add it to the natural log, because then I'm trying to take, trying to add 5 meters to 2 squirrels. You got nothing, okay? So you have to look at, hey, do the units work out? So that answer on number 5 should be around 0.04. It's an ish, but it's going to be around 0.04.
Okay.
So the second one, ironically, is going to be a second order reaction. Okay? So that slope on that second reaction with the NO2 should get you a K value of around 10. Make sure that it has the units on it. Okay? Kevin?
On the K values, specifically for the first order ones at the top, it's supposed to be positive, right? I know the slope's negative, but K should still be positive.
It's kind of, it really doesn't matter. Technically, I will accept either answer, but definitely when you go to put it in the mathematical form,
Yeah, I had it
make
negative.
sure that negative sign is there.
All right.
So your half-life, well, let me back up. Your half-life on that first one up there on number 6 should be around 70 seconds. And the half-life on that second one, number 6, should be a very, very, very bad GPA. What did you get?
8.
Oh, bad.
That's bad, that's bad.
That's a really
very
good
bad.
That's very bad. It's
That's a really good
Justin, do you have an 8?
I know, I was
I have
like,
an 8.
that's
Rose,
like,
do you have an 8? Cohen?
Now, at 1G, I'm going to use you as an example. Okay?
why would you ever?
Because I can. So let's look at the data that you have. So you're starting off at 0.1. 5 seconds later, you're down to 0.017. Okay?
I have a great numbers.
It's a shame.
So here's the deal. First off, this reaction is taking place very quickly, right? Because at time 0, it's at 0.1. 5 seconds later, it's dropped to 0.017. So this thing is taking place rapidly. So, and again, understand what half-life means. It's the amount of time it takes for the initial concentration to become half of what you start with. So if your initial concentration is 0.1, you need to figure out how long it takes to get to 0.05. Well, 0.05 is somewhere between 0.1 and 0.017. So you know your half-life has to be somewhere between 0 and 5 seconds. So if 1G, bless her heart, got an answer of 8 seconds, I said bless her heart. Okay?
That makes it worse.
No, it actually, it makes it better.
Oh.
Makes it sound like you're.
That was the condescending.
So, no.
Bless her
That was so
soul.
not condescending, believe me.
Bless your
Oh, I can be so much more condescending.
Bless her
Yeah,
heart.
I know.
So,
Bless your soul.
8 seconds, right, doesn't not fit the data, because it's outside that time frame.
Yeah.
Okay,
Fun fact, I had the right equation, I just typed in my calculator wrong, so.
bless your heart.
Or bless your heart, Bergkamp.
Whoa. Okay,
Not get too harsh.
on 29,
Okay.
That was a good one.
that should be your first order one, okay?
Okay.
I sure got
We have
it.
to put the order.
How do you,
Your K value should be something times 10 to the -4th,
Okay.
yeah.
okay? And the concentration after 4,000 seconds should be something times 10 to the -2nd.
Is it cool if I didn't put times 10, like I just point 0, whatever?
Yeah, that's fine, but
That was
97.
for.
On 31, that rate constant is also 10 to the -4th,
Yeah.
I know what I did wrong.
and that concentration for that last answer, 2.7 times 10 to the 4 seconds, should be around 0.1.
Yeah.
Okay? Are we cool?
How do you want those written? Like,
There we go.
no, I mean like I have my work on like one side. Do you want the whatever to the left? The equation.
Like the
whatever.
answers?
The equations. The equations.
Like what?
Like the rate constant.
You're just gonna put K equals
I'm
whatever?
the rate law. I meant rate law.
Yeah, you're just gonna put rate law, you can put
I'll,
R equals K times whatever. Yeah, when in doubt, make it clear for me to read. Follow shortcut.
okay.
Boxes go a long way.
On the graphs, make sure I know which graph goes with which problem, okay? Do not randomly have graphs and go, oh, Bergkamp will know which ones they are. No, Bergkamp won't know which ones they are.
Should we like, how do you want us to label them? Like, just like in order?
1, 2, 3, 4.
Yeah, that's fine.
Okay.
Oh, that's what I did.
I put like what the reaction was. I put like A to B graph.
That's fine too. Just don't make me try to guess which ones they are.
But that's the point.
So, put the yellow sheet on top, then the work, and then the graphs last. So yellow sheet, work, graphs.
I guess it's
And then you
picks up
didn't
ads
turn
and
the
shit.
order that you put it in.
Whatever, don't care.
I already took
Why
my
do you
work.
hate it, Chuck?
Whatever, I'm working my clock.
What's wrong, Chuck?
Ow.
Sorry. Supposed to be 0.1.
I'm tired of this round.
is pretty close. Holding on,
My last set was Burkett was saying bless your heart.
Bless your soul. Like a southern grandma.
I know, he's like a sassy southern woman.
A sassy southern woman that was just gossiping at church.
Weirdo.
My biggest, their hair is big and it's teens. Okay.
Oh,
I didn't mean to do that.
Can I do the
No way. What?
please? Can I?
What?
Not right
Okay,
now.
what did you get for the,
Wow.
the very last
It's a
one?
great rainbow.
What?
Bless your heart,
It
Burkett.
didn't.
Bless your heart.
Bless that human taking over.
Okay, I got .13.
Oh my god, my Brian is pretty sassy.
No, you say yellow paper. Yellow
I
paper.
forgot,
wood,
I come in
grass.
Ken's class and
Okay.
he sass for me every school day, and I'm like, I don't know.
Okay. Goodness.
The other day he said, I think if we got rid of Burkett, half the senior class would be a lot happier.
Yeah.
What?
That's
Yellow
what the class
paper.
said.
If what?
Yes, it does.
For the linear.
For the linear one, it has to be.
And a lot dumber.
Something like that. What'd you say? Friday the day talking about Burkett's
yeah.
class. Oh.
Yesterday, no, today. It's every
That's
day.
harsh.
It's every day.
He didn't mean it like that. I think that somebody was complaining about AP Physics.
What'd he
And
say?
Not a true
He said
line.
something
It
about
was
like,
Connor, by
Yeah,
the
we
way.
have-
it was Connor.
Connor S?
Yes.
Oh, dead man walking.
We have a lot of complainers in that class.
Yes, we do.
Every
What,
day.
and it's AP
He
lit?
will put.
Yeah.
Oh, I'm gonna, what
Both.
block is that?
Second.
Second.
Oh, that's my plan.
We're all each other. Say hi.
Every single
I'm gonna have to come in and regulate.
Every
Yeah,
day.
throw hands. Yeah.
Alright.
Every day I see Mr. Pye put both hands on his hips and pop one and be like, what?
Why does,
Uh-uh.
what is that
Hey,
name
what's the
card?
stuff for your meeting? Why
Oh,
can't
this
you
is
put it up on your
Ireland.
fish?
Iceland, first of all.
Oh,
It's like a man on Tinder showing his
I
fish.
don't, okay.
Looking for ladies.
Oh,
How many inches? I don't
I was
like
using it as a straight.
Alright, learn something else.
Today, can we learn about whimsy?
Magic.
About what?
Like you hate the class because you
He's
hate
the
the
weakest
class.
here.
So you hate the class because you don't understand
Do
it.
not, you cannot teach it to us.
So you just hate us, like as people?
Not everyone, but a lot of
You suck, Spoon.
people.
Okay,
No, not people in
So,
general, like.
all I'm
people in
gonna
this
do is
Like-
just show you
Yeah.
where the first order equations come, or first or second order, where the half-life equations come from. I'm not going to expect you to be able to derive these, I just don't want you to think that, oh, it's magic and this is, it's just,
I'm okay.
This is
with
all
that.
magic.
I'm okay
All
with
of it is
that.
magic.
I'm not, no,
We are literally the chemistry fairies.
I realize that,
From Phenol Feeling Magic.
not
I am
disputing that,
so okay with magic.
but
What if you?
that's really not the point. So, if you understand what half-life means, okay, that's kind of the key part of this. So there's a couple of ways you can do it. One is that you could do like smash mouth physics. So, or smash mouth chemistry in this case.
We're doing physics.
Well,
I did not
kind
sign
of.
up for that.
So, so one option is that to derive this formula, you could let the initial concentration of A be like 0.1, okay? You could let that be 0.1. Well, at the end of a half-life, what would be the concentration of A at that point?
0.05.
0.05, okay? Right, because that's what that means by definition. That's what a half-life would be. And then, if you know what the value of K is, then you could solve for your half-life, okay? Right? So you could actually get that number. But we want like a generic one that we could solve for. So, I'm just gonna rewrite this as the natural log of 1/2 A naught equals negative KT times the half-life plus the natural log of A naught. Now, I'm gonna subtract that over. So for those of you that are versed in natural logs, subtracting it over also means the same thing as what?
Dividing.
Dividing. All right, let's hear it for the math nerds in the room. Okay?
Yeah.
So I can rewrite this as the natural log of 1/2 A naught over A naught, right? Equals negative KT half-life. So, what's gonna happen to my A naughts?
Cancel.
They're gonna cancel out. So somebody take the natural log of 1/2.
Should be like negative something gross.
It's like 0.693 would be my
Yeah.
guess.
Oh, what'd you get? Negative 0.693? Let's just
Yeah.
throw that out there as a radical idea, okay? Yay for Sydney. So that equals negative, and I put that 1/2, that negative in front of that because of the fact that it's a negative sloping line, okay? It isn't like a negative of negative. So then to get half-life by itself, oddly enough, I divide by K, which is also a negative value. So the half-life is just 0.693 over K, okay? Now, here's what's important about this. What makes this unique is that this is not dependent upon the initial concentration, okay? So this is typical, like radioactive decay typically tends to be like a first order reaction. So what that means is like, right now, all of you have a certain amount of radioactive carbon in your body, okay? All living organisms do. And it's continuously being exchanged for new. So some of it decays and you eat bread or a sandwich or a candy bar or whatever, and then your body then absorbs some more radioactive carbon-14. Don't flip out and go, oh my God,
Yum, yum.
I have radioactive materials in me, this is bad, okay?
Geiger counter really close.
Yeah.
Why don't I glow?
I know.
All the time.
If I hold a Geiger counter really close,
No.
will it beep?
No. So, there's so many other things that are bombarding you right now. So,
Thanks.
That's
when,
ominous.
when a tree, a squirrel, whatever, stops living, then you're no longer resupplying the radioactive carbon. So if you know how much carbon there was in the sample when it died, and then you can figure out how much of that radioactive carbon still remains, then you can work backwards and figure out, oh, how long ago did this organism stop living, okay? But the beauty of that is that it isn't dependent upon how much there was at the beginning. You just have to make the assumption and go, okay, based upon things that we have studied, trees, squirrels, whatever, on average, this is how much radioactive carbon there is. So then if you can compare that to what you don't have, or what's been left, then you can figure out, oh, based upon this half-life, this is how long it's been gone. Okay. So again, I'm not going to expect you to do this, I'm just showing you where the magic comes from. Okay? Now, if it's second order, we're going to do the same thing. So in the second order, you've got 1 over A equals KT plus 1 over A naught. And we're going to do the same process again. So this is going to be 1 over A naught equals KT plus 1 over A naught.
You're the worst.
Now, all I'm going to do is a little bit of voodoo. I'm just going to take that 2 and flip that up there. So that's going to get me 2 over A naught equals KT plus 1 over A naught. So then, I'm going to subtract this over. So I've got 2 over A naught minus 1 over A naught, which gives me 1 over A naught. I know, crazy talk.
Stop it, you're fractioning
Equals
it.
KT, so then T is gonna equal,
Over What? 1 over
Right.
K.
Yeah.
1 over K. Now,
That was too bad.
I know, where it really was. So again, this is what I preached to you yesterday. In all of these situations, look at the units. So if it's first order, you have 0.693, which has no units, over K. What are the units for K on first order reaction?
1/2.
1/2. So I've got 0.693 and then 1/2, which gets you seconds. Cool. If it's a second order, you've got 1/A0, which is your molarity. But what are the units for K on a second order reaction?
1/2 molarity.
1/molarity seconds. The molarity cancels out. The seconds flip up, you get units of time. So that's why in these things you have to look at the big picture. How do these all fit together? Now, here's how this works out practically. So let's say that I'm going to give you this problem. And I'm going to tell you straight up, it's a first order reaction. Okay?
Great.
You don't have to graph it. I'm going to tell you it's a first order reaction.
Bless you.
Bless your heart. She's never gonna forget.
No, I'm not.
Okay. I could have said it wrong.
I think he's just glad you're assuming he has a heart.
Dang.
Wow.
Dang.
Then he can take.
We're gonna die.
We knew that from the beginning.
Well, he's really mad now. I can't wait till physics.
That's really fun.
That's not, no. Okay,
It'll be fun for me.
Cause he'll get the whole
Huh?
thing. Better class.
Half-life is 20 minutes.
Oh.
Reaction with a half-life of 20 minutes.
I've been looking at it the whole time wondering, wondering what the second one was. I was
What are
like,
we looking at?
first
I
or
don't
Much.
know.
That's an M running into a U.
first or
Are you sure?
That's how much.
Looks like a W. It just has
First
like a-
or
Is it?
or
and then I was about to ask more.
Person.
and then I read it.
What's the, you see B, what's the next one?
intermediate rate constant. How much time is required?
There.
That's mine.
Better.
That's an MU.
Yeah.
Pretty sure.
Okay, so I'm going to tell you straight up, this is going to be a first order reaction. Half-life is 20 minutes, which is kind of slow for a reaction, okay? So just based upon that information, you're going to determine the rate constant, and you can leave it in minutes because you can convert it to seconds, so it's just going to be awkward. So you can just leave it in terms of minutes. And then, based upon that, I want to know how much time is required for 75% of the original concentration to be consumed. Okay? So, let's start with the half-life. Because it's first order, how do you determine the half-life? Half-life equals what?
693 over.
0.693 over
Okay.
K. So you know what the half-life is, that's 20 minutes. All right, got that number. So K is just going to be 0.693 over 20 minutes. What? Nothing.
He made a really silly noise.
Okay, so somebody take 0.693 and divide it by
Oh, I didn't know times.
20. It's going to be a small number.
0.03465.
Point what?
03465.
So call it 3.47. And you can either put this as minutes to the -1, you could put
So,
1 over minutes, I don't care. So now I've got my value of K. So that was the easy one. Now, when you get to B, let's just think this through. So you know that since it's first order, you've got the natural log of A. Now, here's where this negative sign becomes important, because of the fact that even though this works out, the K value works out to be positive, but as first order, that slope has a negative value, so you have to like put that negative sign in there. So I got negative 0.0347, 1 over minutes times time plus the natural log of A naught. So there's a couple of ways you can do this. Let's start with this idea, because you have to start with this idea. You want 75% of this to be consumed. So let's just say, for the sake of argument, that the initial concentration of A was 100. It doesn't matter, it's all going to work out to be the same ratio. But if my initial concentration is 100, then do I put in 25 for A, or do I put in 75? 25, why? Because, so I've got 25 that's remaining, okay? So, I could do 125. I could do that. It's cool, I could do that. But what else could I let the initial concentration of A naught equal? 10?
4 and 1.
Or I could let it be 1. I could let it be 1. What's the natural log of 1?
0.
Oh. Like that one. So, if I let the initial concentration of A be 1, then at this point, the natural log over here is going to be what? The natural log of 0.25 equals negative 0.347 times 1 over minutes times t. Well, conveniently, the natural log of 1 is
0.
So we don't have to worry about that, okay? So, how am I going to get time by itself? Take the natural log of 0.25 and divide that by negative 0.1 over minutes. And what do you get? 40. Huh.
Wait.
Wait.
Since.
Why?
I don't know.
Charles, shortcut. Here's your chance. There's a shortcut to this problem without doing all the math.
Yeah.
Isn't it like half and then half again?
Ah!
it's
So, at the end of the first half-life, okay,
You work for me.
now, there was your chance to have a shortcut.
Well, there was, and I found it. I figured
Okay.
out the way to
Okay.
Yeah.
Charles said shortcut.
So, if the half-life is 20 minutes and it's first
After my
order,
name's
which it is,
The original
okay,
shortcut.
so if I started with an initial concentration of 1, then after 20 minutes, how much is left?
0.5.
0.5.
No, I did.
Then, after another 20 minutes, how much is left?
0.25.
0.25. So all that did was just, this just reinforces the idea of what a half-life is. Okay? Now, a lot of times, it's not going to work out to be that nicely. But it's going to be the same process. So, let's say I gave you this. And I'm going to do first order because that's more tricky than the second order is.
Come back next week. I may be able to pay.
Were you putting it up? Who's your soul dealer?
The devil.
Oh.
Doe went down to Georgia. He was looking for results.
I love
Yeah, he wrote it the other way.
Guess what? I was the fiddle player.
Did you go down to Georgia?
Didn't go down to Georgia.
Here's
Where the devil was. Where the devil was.
Okay, let's see. Why did you go to fiddle?
Is. resides.
Bless yourself.
Is
Oh,
reside-
no.
Oh, talk about the
He's
devil.
just, he's just in Georgia.
All right.
Just vacation.
You're blessed,
Most of the time.
You're
vacation.
blessed.
And he's in
It isn't
Florida.
like I cursed you.
It's such a sarcastic.
Oh,
question,
really?
though.
There was no sarcasm.
Yeah,
No.
You're talking like it was Southern Europe.
Okay. Now, so let's do this as a little bit of a twist. So you run a reaction and you measure the time after 380 seconds, you know that 40% of the reaction has been consumed. I need to find the value of K, assuming that it's a first order reaction. So, start with the basic idea that you have the natural log of A, negative KT plus the natural log of A naught, okay? So, 40% has been consumed. So, what are we gonna put in here? 0.6 or 0.4? 0.6, why? Because that's what's been consumed, right? So we have 0.6 left. Now, if we're clever again,
Wasn't so easy.
what are you gonna let A naught equal?
1.
1. You don't have to. You could let it be 10. You could let it be pi. I don't care, okay? But if you just let it be 1, then, oh, that becomes much simpler. Then you don't even have to worry about it. So then I've got the natural log of A, negative K times, and in this case I know the time is 380 seconds. So you get K as a value of what?
Negative 0.001824.
What'd you get?
Negative 0.001824. It's weird.
1.8.
What'd you get?
I got 0.00134.
I
got what
like that
Jacob
better.
got. Okay, cool. It wasn't my fault this time. Bless
What
you.
units do I have?
1/6.
1 over.
1 over seconds.
1 over 6.
Now, can I find my half-life?
Yeah.
Yes.
Yes.
Now, think about this. Is my half-life going to be bigger or smaller than 380 seconds?
Bigger.
Bigger, why?
Exactly.
At 380 seconds, I haven't consumed half of it. So that's why you can look and go, hey, let's think about what my answer has to be relative to the data that you have.
It can't be
So,
Bless your heart.
so divide that by 0.00134, 1 over seconds, and what do you get?
515.
515?
Happy Father's Day.
If you want to round, I mean, 515.5, so you can say 5.
So call it 515. Here's the point. Does that answer make sense?
Yeah.
Yes, because we said it had to be bigger than
380.
380. Okay? Cool with that. All right. So here's what we have left, and this is something called activation energy. No, we're not.
It would have been so much nicer.
But the good news is we don't have much left.
I know about yeah, and science.
I'm like, oh, whatever. Working, this is the last page of my Bluey notebook. We didn't have magic. I had to play
Louis.
with my yeah.
Well, we're doing the whole integration thing right now.
W show. Greatest show ever.
I'm on the last page. He's drained my Bluey notebook of its life.
I love
I've never seen it.
It's pretty good.
Not sure how.
It's an Australian dog. Abandoned.
I'm gonna keep going.
I didn't know Charles was such a blue.
That was the.
No, Bluey.
That's the yeah.
We're talking
They're all Australian, so it's funny.
But she's still.
I guess it's funny when kids have Australian
She's
accents.
still stupid too.
Dude, it's hilarious. It's a great show.
Yeah,
Peak
they're
show.
just these silly dogs, though.
They're hilarious.
Look, there's a lot of.
They're like
emotions
humans,
here.
but they're hogs.
That's great. That's wild.
Bro, I don't think
I know.
you
That's
know.
why it's a great show. Somebody's like,
You can get this far.
no.
No,
Okay.
they like
Oh,
walk on
no,
their back
I was
legs,
having
like
fun.
they stand up and.
See, Kevin knows what I'm
And then you
talking
broke
about.
these.
I can't believe you had one show.
All right, so let's talk about this
Probably
equation.
better than me.
Y
Oh my,
equals
shut
mx
up.
plus
That's
b.
why it's.
Now,
Stop
this,
talking. You know what this man just said?
what?
I
You
said it
said
might
Bluey
be.
was better than Phineas and
I
Ferb.
said it might be. I said it might be. I said it might be.
This is the most AT Chem conversation of all time.
Does this face look like I care?
Oh, energy
No,
activation.
but it's-
Got it. That's what we're
What does
doing.
any of this?
As a serious crime.
Okay. So, let me explain what this jacked up equation is. It's actually one of the most important.
Do I need to remember that?
Because this is gonna be, if you need it, I'll give it to you.
Okay, that's what I like to hear.
You might wanna write it down because you need it for today's assignment.
Gotcha.
I'm
Wait,
just
what?
saying.
Huh?
The thing up there.
So,
The LNK equals negative
now,
activation energy over
So- and this is how this actually works. Let me explain what activation energy is.
It's in the game.
So, activation energy is how much energy you have to dump into a system to get it started, okay? So, kind of the classic example of this is that I've got a large ball bearing, one wrapped in aluminum foil, the other one is rusted, okay? So, this is a single displacement reaction between aluminum and iron oxide, okay? So, if I just hit these and barely tap them, nothing happens, okay? So you can think of activation energy as being like a bar that you have to jump over, okay? So if you just run up to the bar and go like that, you're not gonna jump over. It's basically thermite on a small scale. So, but if you're going to jump over the bar, if you think of the height of the bar as being activation energy. So right now, I haven't jumped over the bar. But if I hit them together hard enough, okay, then I start a single displacement reaction. So if I'm below that threshold of activation energy, nothing happens. But if I exceed it, then I start a reaction, okay? So you can think of activation energy as being like out, and we're gonna use this analogy a lot as we go through thermodynamics. That's tough to say.
Okay, but what keep it
So here's your
You can't
bar
say it,
that
we
you
can
have
do
to
it.
jump over. So the height of that bar is your activation energy. Now, unfortunately, we have no activation energy probes. It is like, oh, I'll go to Amazon and I'll buy an activation energy probe, okay? They don't exist. Can't measure it directly. But here's what we can measure. So this is going to be the natural log of K, which is your rate constants. So here's what would happen, and this is what you're going to do in the lab. You're going to run reactions at different temperatures. And if you look at a simple idea that R equals K times like a first order reaction, well, as you change the temperature, that's going to change your rate. If it's very cold, the reaction takes a long time. The rate's going to be a very small number. K would be really small. If you heat up the situation and you make it run at a higher temperature, the rate's going to become a much bigger number because of the fact that the reaction's going to happen much faster. And then the only way that can work is if the K gets bigger. So your rate constant is dependent upon temperature. So what you would do, and this is, again, you're going to do this in the lab with iodine. So you're going to run reactions at different temperatures. And then you're going to determine the K values at different temperatures. So in terms of how this plays out, this is just in the form of y equals mx plus b. That's all it is, okay? It looks completely jacked up, but this is all it is. It's a linear function. So what this means is that on the y-axis, you're going to plot the natural log of different values of k, okay? So you would have to have, hey, At 100 degrees Celsius, this is the value of K. At 200 degrees Celsius, this is the value of K. So you would have to be given data with temperatures and what the values of K are. Now, down here, you're going to plot the inverse of temperature, but it has to be in Kelvin. Everybody cool with how you convert from Celsius to Kelvin?
Plus 278.
At 273. So if you're like at room temperature, right now this is about 20 degrees Celsius. You add that to 273, you're going to get 293. So this is where the magic works in terms of units. So this graph is going to come down here like this, all right? So if you look at what happens with the units, you got change in y over change in x. Because you're taking the natural log of k, and k doesn't have, so it doesn't make any difference if it's 0 order, forced order, it doesn't make any difference, because you're taking the natural log of it. So up on top, you have no units. So then down here, you have units of 1 over Kelvin. So the units for your slope then work out to be Kelvin. But here's the weird deal. Even though the slope works out to be Kelvin, it isn't the temperature. But what's important is that the units are Kelvin. And we know it's not the temperature because the temperature is continuously changing. But the units are Kelvin. Okay? That's the whole point of that story. So this is going to be equal to your slope. So what you're after is the activation energy. So your slope is going to equal negative E sub A over R. Now, R is your ideal gas law constant. And this will make sense in just a second. And there's two different values of R. In this situation, you've got to use the 8.314 joules per mole Kelvin. Don't use the one that's in atmosphere liters because the units will be a train wreck. Okay? So, you're going to find the slope. Okay? You're going to draw a graph and you're going to find the slope of that line. Boom. So you're going to know the slope. You're going to know what that number is. You know what R is because that's the ideal gas law constant. So this is where the units are important. So you're going to take that slope, which is in Kelvin, okay, and it's also going to be a negative number because it's going to be line